Thank you.
Oh, no problem. Hey, I like the easy problems, or the ones that are completely broken so I can fix it. I don't like the ones where it's like the car.
So let me fix this one, and then we'll go back to these slides quickly. So for the concept for this one, how do we use this cut to make the two, to bisect the entire cross-section? For this one, is no way. Right? So our concept we have learned so far since we start here for this kind of problems. So for this kind of the box fin, and we call the box cross-section shape, that is very little bit standalone question. So the focus today, the first part, is go over this kind of questions. And to go for these questions, let me think about what is the best way to do it.
Why don't you take your I out the Y line, basically? Or just rotate
For these questions, we can try is this. And here today, I make a few teaching aids. So let me revise the problem to accommodate my toys. And yes, so for example, here we like to try is, I want to calculate the tau AA here. Okay, and maybe the AA, let me draw it in good way. Okay, we just like this. Maybe I can give some dimensions.
Wait, is that the same tau A as earlier?
Let me make one example. So say if we have the cross section, this is 12, this is 12, and square, and inside is also square, and this is 6, and here is 6. So basically for each side that is 3, 3, 3, 3, 3, okay? So for this case, for example here, our transverse loading is in this direction. And say
Given to you, or is the V given?
V is given. And say for this example, we want to calculate, for example, the stress. For example, this is AA. We want to calculate tau AA. And to make this work, we have to really find the cut that can bisect the whole entire cross section. So for this purpose, I will make the cut is symmetric to here. So that is here. So in this way, I additionally pick this one. So this one, AA, this segment, plus this one, that can make the whole entire cross section into two portions. And for me, I simply calculate, I pick this upper portion for my Q. Okay, and that's a strategy. And for this case, we calculate Q. For example, for in this dimension, this is 12, and this is 3. Centroid from this to the neutral axis. This is 3. 3 by 3 plus 1.5 is 4.5. So the y bar is 4.5. The area is 12 times 3. So for this case is 36 multiplied with 3.5, 72. Is that right? No. 108.
162.
162? Okay, and for our equation, tau equal to VQ over IT. And then for this one, we can calculate I for the first I will be the bigger one and minus the middle one. Okay, so for this case, I will be equal to 112, and the bigger one is 12 times 12 to the cube, minus the smaller one is 6 times 6 to the cube. Okay, so I don't have a calculation. I don't have a calculation there, so leave it. And then for this case, what is T? Thickness of what?
Is it 3?
Of the
Of
section.
3 or
6.
so 3, 6, or 12.
Oh, it's 3.
Count both sides.
So we now come to the point. For what we have learned, we know that for this case for sure, T is the thickness of the cut. That one, right? For this case, again, we stick with our original concept. The T should be the thickness of the cuts. This one and this one. So plus together is how much? 6. And I know at this moment some of you have thinking, that's a little bit weird. Okay, I will answer that question to you right away. And we back to here. Let me finish this one. So basically, tau will be equal to whatever the V we are given. Q we calculate the 162, and for I whatever that number is, and by 6. So that is the average of the tau A. No, this is the average stress. This is the average stress happening in this area and in that area. Okay, so that is the average stress. You remember this average stress representing is back to our model here. That one, basically average stress representing is the total force divided by the area we cut. And now for here, for this case, we have 2 areas we cut. So the average stress here representing is the average stress over this area and that area. If for this example, the 2 sides are symmetric, I mean respect to the center line, and they're the same area, so basically this average should be equal to this one we're looking for.
So you don't have to divide it or anything?
So we don't have to divide. On the other side, so that is this case I tried. So this is the box, okay, this is a box. And then from here you can see this is a side AA, and this is the additional cut we make and trying to calculate make the dash area for Q. So in this case, what we calculated, this average representing is the total force divided by this area plus this area. The total force divided by the total force, which means H. H divided by area. Area is this one plus this one. And that representing is the average stress over the combined area. If the 2 areas are the same, basically that the average stress should be the same here or there. On the other side, if unfortunately the 2 sides are not equal, then that would be the question. Because in here we're asking, for this case, is the average stress over the 2 combined areas. However, the 2 areas basically play the different role in contributing the force, right? So this is the average over the 2, for example, say, for example, if you could imagine we have the virtual reflection of our classroom outside the window. And say here we have, right now I believe here could be 50. And on the other virtual side has a 50. So the average students per square foot will be the same number here and there, right? However, if say on the other side, some students, they have fallen to sleep and the spirit just begun, so they have, so they have a less number than here. So in this way, the total number of the students both sides will be less than it should be, but the same footprint. So here we take the average of the whole Q size is less than it's supposed to be, right? The same concept. Here is this side, there is this side. So this representing is the total average number based upon the two sides, based upon two footprints. But that is not really representing, is that really supposed to be go to here. So to this point, I make one note is this. This technique would be good, would be correct if the cut is symmetric, the area the same. Like this case. Okay, the symmetric with respect to the center line, and the both has the same area, the size of the area. I mean, the area is the underneath there. Okay. For this case, unsymmetric, then this technique is not good anymore. They won't give you the right answer. So now I want to talk about today is how do we calculate this to calculate this kind of these things. So let me make into this one. To solve for this problem, I want to introduce the concept of the shear flow. Okay, remember from the beginning when we derived these equations, we have three things. One is the delta H. Delta H divided by that area, and that is what we obtained here, and that is VQ over IT. And at that time, we defined the delta H divided by the X, that is called the shear flow. And the shear flow, let me pick my model first. This is the total cut we make, that is the area, and under which the delta H is here. If the length, if the cut length from here to here is called L, so simply H divided by L equal to Q. So for example, if the shear flow, if the shear flow is Q, and if the unit of this cut is 5 units, then total force here H equal to 5Q. Okay, so that's the concept of the shear flow. Shear flow simply is the force per unit length. Okay, so per unit length. So if we want to solve for that problem, so we have to use the shear flow. So basically here, what we are looking into the problem is this. Again, this is our beam. We back to our original thinking. And for example, if this clamp and this is the point loading, and we know that at this cut and at this cut, the bending is different, not pure bending anymore. Because not pure bending anymore, and then using our homework of chapter 4, we realize the total force on this side is not equal to this side. So that means we have the force here to get in static balance. So that is the whole idea, and that coming into these equations. This is a cut we make. We can make any internal cuts. Okay, as long as we can make any internal cuts, then we can always calculate the delta corresponding delta H. Divide the H by that corresponding area, that is the cut. And now we can cut any type. So instead of making the one cut in on the other side is, okay, that is a cut like this. And the other option we can choose is this one. I cut it cut into this way, so that means you can see right now, instead of making one horizontal cut, I make this one. So that means in this way, exposed has two internal cuts, is one red one here and black one here, right? You got it? So that means the same concept, as long as you can calculate Q corresponding to this area, respect to the neutral axis, then you can calculate corresponding value of the Q, right? So that's the Q. You put into this formula VQ over IT, then that is the average shear stress over where? Over the two combined cut areas. Okay? In this way, you can see that is average over the two combined. However, that doesn't represent is the average here or the average shear stress here. Okay? So this result is the final step of the calculation. If we really want to find out what is really the average stress here and here, then we can go one step. The earlier is this. Say we make a cut and we know that they should have the shear stress. They should have the shear force delta H. The same rho of the delta H over on here and on here, right? So why not we say the delta H is here, delta H1 and delta H2. On this side is H1, on the bottom side is H2. Definitely, H1 is not equal to H2 in general. If we are able to solve for the value of H1, and then we divide H1 by this area, and that will be the average shear stress, right? If we can solve for this, the H on this area, then that represents is the average shear stress on this area. So the issue is how to solve for H1 and H2. Or equivalent to say, if this will be the unit length, then how to solve for Q1 and Q2. Are we good? Yes.
And so we do that so we can come up with a ratio that then can be applied to the entire object.
The ratio of,
We're coming up with an average that can then be applied to the whole spectrum,
Yes.
whatever it is.
yes, the same concept should be able to apply even to this case. Okay. So now again, the shear flow, once we make this cut, and basically here is one vertical cut and horizontal cut. Okay, that is mean. And then shaded area corresponding is based upon this cross-sectional area to calculate for Q. And now we know the shear flow along this red and along this black are different. As long as we can solve for Q1 and Q2, then we can divide the Q using the Q to calculate the shear stress. Is this. Once we have Q, then tau will be equal to Q over T. Okay, so basically Q equal to VQ over I. So again, once we know the Q here and here, we simply divide. For example, say if the Q on this edge is Q1, then I simply divide the Q1 by the corresponding thickness here. That is this dimension. So Q1 divided by this dimension, that is T. Then that is the average stress. If this is the Q2 shear flow, Q2 divided by corresponding dimension, which is this T, then that will be the the average shear stress on this side. Will be okay? So this is the concept, and then the video is taken. So basically, you can rewind and go read this one. So now we stick with this concept, and then I'm going to use the numbers to calculate for something, and then we can exercise.